Hello my dear friends, I hope all of you are doing good. In my previous videos, we have seen some of the fundamental concepts of this subject, compressible fluid flow. In my first video, I have introduced you the concepts of thermodynamics like the continuum approach, the systems approach and control volume approach. In the second video, we have discussed about Mach number, the steady flow energy equation and the stagnation conditions. We have talked about the stagnation conditions like stagnation enthalpy, stagnation temperature, stagnation pressure, stagnation density and stagnation velocity of sound. And in the third video, we have seen some of the very interesting facts in this subject. We have classified the flow regime into 5 based on Mach number. We have classified into incompressible flow, subsonic flow, transonic flow, supersonic flow and hypersonic flow. We have also seen the wave propagation pattern in all these kinds of flows. And today, in this video, we will be discussing 3 derivations. The continuity equation, which is also known as conservation of mass, the momentum equation, which is also known as conservation of momentum, and the energy equation, which is also known as conservation of energy. Let us start the proceedings with continuity equation, which is also known as conservation of mass. So conservation of mass says mass can neither be created nor be destroyed. Consider a streamline like this. Now, this is the system at time t. The blue circle represents the system at time t. Now, after some time, say time dt, we are drawing the same system. So this is the system after some time. So this is the system at time t plus dt represented by the green circle. Now in this figure we can clearly mark 3 separate regions. Region 1, which happens to be the intersection of these 2 circles. Region 2, which lies entirely in the green circle, and region 3, which lies entirely in the blue circle. Now, as per the conservation of mass, as I told before, mass can neither be created nor be destroyed. Therefore, mass at time t and mass at time t plus dt will be the same. So, what is the mass at time t? So, at time t, which is represented by the blue circle, we have got 2 different regions, region 3 and region 1. So, m3t plus m1t, that is the mass which happens to flow in time t, which will be equal to mass at time t plus dt. Now, what is the mass at time t plus dt? That is represented by the green circle. So, this is equal to m1 of t plus dt plus m2 of t plus dt. So, mass at time t and mass at time t plus dt both are the same. And we are rearranging it in the next step such that all the ones comes to the left hand side of the expression. So, m1t plus dt minus m1t is equal to m3t minus m2t plus dt. And in the next step, I am going to divide the entire expression with respect to dt. So, this is our equation number 1. Now, I am going to define these 3 terms separately. Let us start with the expression on the left hand side. So, if you closely watch the expression at left hand side, you can understand that that is nothing but the rate of change of mass within the control volume. Now, what is the control volume in this case? The region marked by 1, it is the control volume. So, what is its rate of change of mass? That will be equal to the final mass minus the initial mass divided by the time taken. So, here in this expression, as we know, that is equal to m1 of t plus dt, that is the mass in the final stage, minus m1t, that is the mass in the initial stage. So, that the difference will give you the change of mass, and we are dividing it with respect to dt. So, that will give you the time rate of change of mass within the control volume or the region represented by 1. Now, moving on, let us try to define the first term on the right hand side. m3t by dt. So, m3t that happens to be in the first circle or the blue circle. So, that is nothing but the mass entering the system or inflow of mass flux. So that is equal to integral In represents into the system, in, of dm dot. M dot is nothing but the mass flow rate. Similarly, the last term on the first equation, that is m2 of t plus dt by dt, that is the mass moving out of the system. So that is equal to integral out dm dot. Again, m dot is nothing but the mass flow rate. Now we have got three expressions, equations 2, 3 and 4. We are going to substitute it back to the original expression, equation number 1. So this is our fifth equation. Now we can read this equation as the rate of change of mass within the control volume is equal to the difference in rates of flow of the incoming and outgoing masses. So that is how you can read expression number 5, because the first term, dou by dou t of mCv, that is the rate of change of mass within the control volume, which was represented by the region 1, is equal to the difference in rates of flow of the incoming, that is integral In dm dot, and the outgoing, that is integral out dm dot. Okay, so this is again our equation number 5. Now we are going to define these three terms in another way also. So let us start with the first term, that is dou by dou t of mCv. You know, m, the mass is equal to density rho into volume V. So dou by dou t of mCv means mass within the control volume, is equal to dou by dou t of integral Cv rho into dV. Again, rho is nothing but the density and V is the volume. Again, you can rearrange that expression, which will give you integral Cv of dou rho by dou t into dV. That is our first expression. Now let us try to define the next term, that is integral In dm dot in equation number 5. So that is equal to, we know the expression for m dot or mass flow rate is equal to rho c into A. So integral In or in dm dot is equal to integral in rho c dA, change in area. Similarly, the last term in expression number 5, integral out dm dot is equal to integral out rho c dA. Now we are going to substitute the equations 6, 7 and 8 back to our original equation, equation number 5. So this equation number 9 will give you the new expression. Integrals on the right hand side in this equation, equation number 9, represents the quantities at the entry and exit. Now we are going to change this entry and exit to 1 and 2 respectively. So the first term on right hand side, that is integral In rho c dA, is equal to, I am going to substitute 1 for in. So that will be equal to integral rho 1 c1 dA1. Similarly, the next term, integral out rho c dA is equal to integral rho 2 c2 dA2. Now again, I am going to substitute back these expressions 10 and 11 to the original equation, equation number 9. So we will be obtaining like this. And this is our expression number 12. We know for a steady flow, the properties won't change with respect to the time. Therefore, dou rho by dou t, that is the rate of change of density, will be equal to 0 for a steady compressible flow and as well as for an incompressible flow. We know for an incompressible flow, there is no change in density. So the expression number 12 can be rewritten as follows, because the term on left hand side is equal to 0. Integral rho 1 c1 dA1 minus integral rho 2 c2 dA2 is equal to 0. After performing the integration, and we can rewrite the above expression, we will be obtaining as rho 1 c1 a1 is equal to rho 2 c2 a2. We have performed integration on the variable a and we have rewritten. Or in other words, I can say rho AC is a constant, and this term rho AC is nothing but the mass flow rate. So the law of conservation of mass or the continuity equation states that m dot or rho AC is a constant, and this is the continuity equation for the one-dimensional steady flow. Having done with the continuity equation, now let us move to the second derivation, that is the momentum equation, which is also known as conservation of momentum. We are starting with Newton's second law of motion. which states that the rate of change of momentum in each direction is equal to the algebraic sum of forces exerted at a certain instant. We are considering the same figure which we have already seen in the continuity equation. I have marked the two components of velocity, Cx, the velocity component in x direction, and Cy, the velocity component in y direction. By Newton's second law, the sum of forces in x direction is equal to dou by dou t of mcx. What is this mcs? Mass into cx, the velocity in x direction. So mass into velocity is nothing but the momentum. So rate of change of momentum is equal to the sum of forces in x direction. Okay, now the following steps are exactly similar to what we have seen in the continuity equation. We have again defined the three regions 1, 2 and 3. Momentum at time t will be equal to momentum at time t plus dt. Therefore, mcx of 1t plus mcx of 3t, that is the region represented by the blue circle or system at time t, is equal to mcx of 1t plus dt plus mcx 2 of t plus dt. The term on right hand side represents the momentum represented by the green region or system at time t plus dt. Now again we are performing a rearrangement such that all the ones go to the left hand side of the expression. And in the next step we are dividing throughout with respect to dt. So this is our equation number 2. And next we are going to redefine the three terms which we have already seen in expression number 2. So let us start with the first term. As we can see, or as we have already discussed in the continuity equation, that is nothing but the rate of change of momentum within the control volume or the region represented by area 1. mcx 1 of t plus dt, that is the momentum in the final stage, minus mcx of 1t, that is the momentum in the initial stage. So the difference between these two will give you the change of momentum. If you are differentiating it with respect to time, that will give you the rate of change of momentum within the control volume or within the region 1. Next, let us see the first term on the right hand side, that is mcx of 3t by dt. So that is entirely in the region represented by the blue color. So that is nothing but integral in cx dm dot, or the inflow of momentum flux, the momentum entering the system. Similarly, the last term, that is mcx2 of t plus dt by dt, that is the momentum exiting the system, and that can be seen in the region represented by the green color or by the system at time t plus dt. That is equal to integral out cx dm dot, that is the outflow of momentum flux. Next, as usual, we are going to substitute equations number 3, 4 and 5 back to our original expression. That is the expression for the Newton's second law, which states Fx, the sum of forces in Fx, is equal to dou by dou t of mcx, that is the rate of change of momentum in x direction. So we are substituting equations 3, 4 and 5 in this equation. And here we can see the expression number 6. This expression can be read as the algebraic sum of forces acting on the control surface in each direction, in this case for the x direction, is equal to the rate of change of momentum within the control volume, that is the first term in the right hand side of the expression, plus the excess of outgoing momentum flux, that is the second term in the RHS, over the incoming momentum flux, that is the final term in the right hand side. So this is how expression 6 can be read. In the next step, like the continuity equation, we are going to rewrite all these terms. Let us start with the first term on the right hand side, that is dou by dou t of mcx within the control volume. You know, mass is equal to density into volume. So in this expression, instead of m, I am going to substitute rho into dv. And after performing the rearrangement, we can see as in the question number 7. Now let us move to the second term on the right hand side, that is integral out cx dm. Here we are going to substitute, instead of m dot, we know m dot is the mass flow rate, which is equal to rho ca. If it is dm dot, then that will be equal to rho C dA for out. This is the momentum flux of the outgoing part. And the last term, integral in Cx dm dot, will be equal to, again, instead of m dot, I am going to substitute rho Ca. So this is the expression number 9. And now I am going to substitute expressions 7, 8 and 9 back to our expression number 6. So this is the new expression and it can be represented as 10. As we can see, this is the sum of forces acting along the x direction. The same expressions can be rewritten for y and z direction. Instead of the suffix x, we have to substitute suffixes y and z. So this is the sum of forces for y and z directions respectively. And now coming to the last part, for a steady flow, we know the rate of change of density will be equal to 0. No properties change for a steady flow. Therefore, the term dou by dou t of integral rho C dV will be equal to 0, simply because dou rho by dou t is equal to 0. Hence, the equations for the forces can be rewritten as like this. We are neglecting the first term in the previous case because that term has got the rate of change of densities. For one-dimensional flow, we can neglect x, y, z terms and we can substitute it with 1 for entry condition and 2 for exit condition. And hence, for a steady one-dimensional flow, the sum of forces will be equal to rho 2 A2 C2 square, because here we have got two terms for C. It was Cx, Cy and Cz. But for a steady one-dimensional flow, as I told before, you don't have to consider x, y, z dimensions. We have got only one dimension. So sum of forces for a steady one-dimensional flow will be equal to rho 2 A2 C2 square minus rho 1 A1 C1 square. And this expression is known as the momentum equation. And finally, we are moving to the last derivation of the day, the energy equation, which is also known as conservation of energy. You know, from the first law of thermodynamics, the heat transfer dq is equal to dE plus dW. We are going to differentiate that with respect to dt throughout, and the two terms on the right hand side have to be rewritten. Let us start with the term dE by dt. The change in energy dE by dt is equal to the time rate of change of energy within the control volume plus the outgoing energy flux minus the incoming energy flux. And this is exactly the same thing which we have already seen in the derivation of conservation of momentum. Therefore, dE by dt is equal to dE by dt within the control volume, that is the time rate of change of energy within the control volume, plus the outgoing energy flux, that is integral out E dm dot minus the incoming energy flux, that is integral in E dm dot. So that is how we deal with the first term on the right hand side. Now moving to the second term on the right hand side, that is the work term. As we know, for a flow process, the work term includes two things, the flow work and the shaft work. Flow work is nothing but the pressure volume work, and we have also got a shaft work which is indicated by Ws. dW by dt is equal to integral out PV dm dot, that is the outflow of the pressure volume work, minus integral in PV dm dot, that is the inflow of the pressure volume work, plus of course the shaft work, that is dWs by dt. Now we are going to substitute these two expressions for the main expression. Hence, the expression for dq by dt can be seen as like this. Now there are some like terms, so we can rearrange it, and hence dq by dt will be equal to dE by dt of the control volume CV plus integral out E plus PV dm dot minus integral in E plus PV dm dot plus dWs by dt. Ws is nothing but the shaft work. And we know the total energy in a system is the sum of three energies: the internal energy, pressure energy, and potential energy. Therefore, in specific terms, the energy E is equal to U plus half, there is no m because we are dealing with specific terms. So half c square, the kinetic energy term, plus gz, the potential energy term. We are writing in terms of the specific values. Therefore, E plus PV, we are adding PV to the left hand side of the expression, and hence PV has to be added to the right hand side also. E plus PV is equal to U plus PV plus half C square plus GZ. But we know U plus PV is nothing but the enthalpy H. Therefore, E plus PV is equal to H plus half C square plus GZ. And that is the expression number 5. And now we are going to substitute this expression number 5, back to our original equation number 4. So dq by dt is equal to de by dt of Cv plus integral out h plus half c square plus gz dm dot. So the substitution has been made there, minus integral in h plus half c square plus gz dm dot. And here also we are doing the substitution, plus dws by dt. Okay, for a steady flow, we know that there is no change in any of its properties, and hence dE by dt will be equal to 0 because time rate of change of energy will be equal to 0. Hence, the first term on the right hand side of our sixth expressions can be neglected. And this is how the new expression look like for the steady flow. For an adiabatic process, we know there is no heat transfer. Therefore, the value Q is equal to 0, and hence dQ by dt is also equal to 0. So the term on the left hand side for the expression number 7 is also getting cancelled. And this is the new expression. We have rewritten in such a way that dws by dt has gone to the left hand side. Now, for a one-dimensional and steady flow, as I told before, if you are considering the one-dimensional flow, instead of in, you can write it as 1, suffix 1, and instead of out, you can go for suffix 2. So, the expression 9 will be the expression for one-dimensional steady adiabatic flow. And for gases, there is no meaning in considering the altitude. So, Z1 and Z2 are the same. So, the terms GZ1 and GZ2 gets cancelled. And we know the term H plus half C square, that is nothing but the stagnation enthalpy H0. So the expression can be rewritten as dWs by dt is equal to m dot into H01 minus H02. And finally, if the shaft work is absent, that is, if Ws is equal to 0, we can write it as H01 is equal to H02. That is, the stagnation enthalpy remains a constant, which we have already seen. And this expression is known as the energy equation or the conservation of energy. And with that, we are ending today's session. We have seen 3 different derivations: the continuity equation, the momentum equation, and the energy equation. I would say the continuity equation is the basis of these derivations. If you can correctly understand the continuity equation, the other 2 equations are very easy. That's all for the day. Thank you and have a nice day.